Hello everyone, we'll be talking now about our RISC-V Big-endian adventure. So first off, I'm going to start off with who we are and why we did this, and a bit about how Big-endian works on RISC-V. So we're from a company called Codethink. We're an open source consultancy based in Manchester, UK. The speakers are myself, Lawrence Hunter, and Roan Richmond, who will be covering some of the work later on. And we also worked alongside two other engineers, Ben Dukes and Nazar Kozakov, to do this work. So why are we doing Big-endian on RISC-V? We thought it'd be a technically challenging experience and would be quite fun. So we wanted to add support through the Linux software stack and then run it on QEMU and CVA6, both which would require modification to do so. And we were also challenged in our company's past to do this for ARM32, and this led to some very interesting projects and clients. But finally, we thought it would be fun. It was an R&D project, and it was fun. So how does Big-endian work on RISC-V? So the CSRs control this endianness level. There is a machine, supervisor, user, and hypervisor, but we didn't focus on hypervisor, each of which can be independent, and they're controlled by bits 37, 36, and 6 in the MBE, with the S status being a subset of the M status. The endianness is only applied to data. Instructions always remain little endian, and these bits can be changed at runtime through CSR writes. And the MMU also always follows the supervisor level. So what does adding Big-endian support actually look like? So we started with QEMU. QEMU is a great target. It's very easy to add in tracing and to debug. So to do that with QEMU, we needed to add the ability to modify the M status to be able to write through the CSRs, and then that CSR value to do something. We also then modified OpenSBI to allow us to boot into Big-endian. We needed to modify Linux to build for Big-endian, and we did this through modifications to build root. And later on, which Rowan will cover, we modified CVA6 to allow Big-endian operation. So I'm going to delve in a bit deeper into the software stack. So first off, we faced common issues across the software stack. RISC-V has been little endian pretty much the whole time. So software tends to assume it's little endian rather than being explicit. Quite a few projects made use of the byte order macro, which allowed this change to be quite simple, and we could do so at build time using this macro. The memory mapped I/O buses are also always little endian, so we needed to ensure that that remained, and alongside the instructions, which are again also little endian. So over here, we ran into a few problems, mainly around the assumed endianness, and the fact that some RISC-V instructions over time have been hand-assembled rather than being done properly. So introspection and code generation needed changing, but this largely came down to where .word had been used rather than .instruction, and so then the data was treated as data rather than an instruction, and the byte ordering was not respected. This also has an extra benefit that it means they are marked as instructions, so they're clearer when looking through tools like kmutools. Another problem we faced is around data decomposition. So when the endianness is changed, the fields in a word move around. So if you look within a word, it won't be where you expect it to be. So this can mean the need to rearrange structs. You can see an example here where basically it just gets swapped, because if you didn't, you'd be reading the wrong value. And this was quite common in networking and acceleration code. With QEMU specifically, this was our first target. I mentioned a bit before about how we needed to do the CSRs. So we needed to be able to control it for each execution level. In RISC-V, these are allowed to be independent, and you can have supervisor, machine, and user be different endianness levels. Here, we've mainly kept it the same, which is also allowed for them to be identical. So we added the CSR write, which mainly meant modifying the masks to allow writing to the MBE and SBE bits. And we also then had to modify again the mask on the S status to propagate the subset of the M status register. so the endianness was visible. And we made it so that the memory operation should observe the CPU's context Big-endian flag, and we took advantage of QEMU's existing memops to deal with the Big-endian loads. We also then had to do further consideration around the ZACAS extension, which is the atomic compare and swap, but this just basically meant a bit of duplicated effort on that part. The floating point operation was the same, but we also had to update the page table code to follow the S mode as per the specification, and we had to, so you can see an example here of what that bit looks like. It's basically defined in the CPU configuration. A bit more on OpenSBI. So we needed to update the build to allow us to build a Big-endian version, but we decided it was much easier to keep OpenSBI in Little-endian and take advantage of the runtime switching. So we started in Little-endian, and then when we hand off OpenSBI, hands off in Big-endian instead. And to do this, we needed to have the option to set the S status bits, and we also needed to maintain the IO code's endianness. With the kernel, we had to remove optimized instructions, optimized routines. These did not map well to Big-endian, and it was out of scope for us to modify them to do so. And the kernel also had to be modified alongside similar problems faced in other projects around its instruction modification and introspection. So this was things around the K-probes, the BPF, and static branches, as well as trap codes. So this is roughly the changes we made to the software stack. So I'm going to pass off to Rowan to talk to you more about the changes we made to CVA6.
Cool. I'll talk to you about some of the changes we had to make to CVA6. But before I talk about the actual changes, I'll talk about the setup. So that's the build and testing setup we used for this. The testing setup. So we used some of the Genesis 2 boards. We had a few of these, and these are basically attached to developer laptops. And then on the developer laptops, you could then run OpenOCD and GDB. And using this combo, you could basically flash small assembly programs into memory, and then reconfigure the program counter to point at these, and then step through them one by one. This basically meant that we could run individual instructions in Big-endian and in Little-endian, and then look at the register state after each one, as well as extracting some of the memory state as well, which is obviously very useful when debugging. Then after we were happy with all the instructions working, the idea is then to test by booting Linux, a Big-endian version of Linux and OpenSBI. For building this, we use the Xilinx toolchain as we're using the Genesis 2 board. And this we packaged up in a container. This allowed us to spin up developers easier. As well as this, in this container, it had all the correct packages already installed in the correct locations, which just saved a lot of time, as we were running most of this on our laptops, which are Linux-based machines, and some of that gets quite complicated. And as well as this, we used the X11 pass-through, so that when you download this container and you're running in the container, you can still use some of the GUIs. Cool. So onto the changes. The unsurprisingly focused around the memory operations. So the simple changes are into load and into the store unit. So into each one of those, because they're separate units in CVA6, we added a combinatorial block. And this basically does byte swapping based on the MBE value. The MBE value is forwarded from the CSRs back to these stages. And then you basically check and then do optional byte swapping. As well as this, we also do sign extension in parallel for this. This basically just means that you don't have to do them one by one, and it speeds up the whole process slightly. One of the interesting issues we had with this when we were just getting going, so these simple changes, we thought they'd be quite easy to do. And then when using OpenOCD and GDB to flash these small assembly programs, what happened was we saw OpenOCD crashing and being unable to connect to the board. So we were switching to Big-endian, trying to execute a load or store instruction, and then we would see OpenOCD crashing basically. And we thought, oh, we're clearly doing something wrong in our changes. And what actually it turned out to be was an issue in OpenOCD being unable to handle this target being in Big-endian. And so I think we're going to open a ticket today for this. And then, so for this, we didn't have much time to look into it any further. So what we had to do for our small assembly programs where we're testing individual instructions is we have to turn back to little endian mode after, so we can still look at the register state. Another of the issues that we thought we might encounter is the fact that we're using a forwarded MBE value in our load and stores, and this could possibly cause like a read before write error. So if you have a CSR write to this endian bit, and then immediately following that you have a load or store instruction, you could basically miss the right MBE value. And upon further reading of the spec, this is kind of handled by the spec. As any change to a CSR register, you're meant to do a fence operation, which should flush the pipeline anyway. So it means you're kind of okay for this. And if you don't do this, then it's kind of undefined behavior anyway. So in effect, we have ignored this issue, or well, to keep it simple, we've passed over this issue. And for the atomic operations, which are some of the harder operations to implement, we initially thought we'd have to do the byte swapping inside CVA6. However, the AXI bus actually supports doing big-endian atomic operations. So what we did instead was we expanded the interface, allowing you basically to pass through the big-endian bit, and therefore do the big-endian operations along the AXI bus. So those are kind of the changes we've done to CVA6. There's also some page table changes we had to do as well, but those aren't major. And so I'll quickly talk about some of the upstreaming efforts and some of the problems that still exist for this. So as you can see, there are still some problems listed on the screen there. And we conducted this work mainly as an experiment and a kind of technical exercise. So this is the kind of state we're leaving it in. All of our patches do work, and they're all quite clean, but there are some libraries we haven't fully looked into. So we're leaving those as open bugs. And for the upstream communities, a lot of the communities said they don't really want to maintain this work because it's quite a niche use case. So with sponsorship and with use from industry, we might be able to continue this, but for now, we're going to have to leave it where it is. Awesome. And then on the next slide, if you want to have a look at any of this work, there's a QR code you can scan there, or you can visit the URL listed at the bottom there. Awesome. Any questions?
So with the bitmanip extension, kind of maybe give some of the byte swapping things that you might need, but what are the shortcomings that like I don't know, like it seems like you could maybe use bitmanip to get around this, but maybe that doesn't cover all the use cases.
Yeah, so there is the ZBB extension, which is for byte swapping specifically. So if you're just doing a small amount of big-endian operations in like a very concentrated block, you can obviously use the ZBB. But if you're doing more extensive big-endian operations, this kind of allows you to switch into big-endian mode for a short period of time, do all of your big-endian operations and then switch back. Or if you're just booting big-endian kernels, this is more applicable rather than having to swap on every single instruction.
Okay, thank you.
Anyone else?
My comment is coming from an ex-big-endian person who I was at IBM on Power, which was big-endian. We made the switch to little-endian. My question is, what is this for? Because we didn't change from big-endian to little-endian willingly. It's just the software ecosystem was so full of software that had little-endian baked into the things. We couldn't. There was a never-ending job to port all of these fixes to make them bi-endian.
Yeah.
You're going to have to deal with that if you go to this. I mean, so what is the big reason for you wanting to go to big-endian?
So the advantage of this basically is that you have configurable runtime endianness. So you can be running a little-endian kernel, and you can then switch for user space. Within the spec, basically, allows the switching for a user space for a short period of time into big-endian. So you don't have to do all that porting for everything. If you've just got a small subset of things that are already in big-endian and you want to use big-endian for those subsets, you could do it then. But this was more done as a technical experiment, and then for some of the networking protocols that are still using big-endian.
The code that we were having problems with, it wasn't necessarily written to be little endian. It just was little endian. It should have been bi-endian. It should have just worked. You can write code that will work for both little endian and big endian.
Yeah.
But it wasn't.
Yeah.
So
So how much of like the use case that you just said, like user space in Big Endian is like, from my perspective, coming from the networking background at Cavium where we made MIPS that was Big Endian, we transitioned to ARM and Linux, which is little endian, and basically all our customers went with that.
Yeah.
You know, so even in the networking space, you know, Big Endian is not an actual. It used to be a business case. I just don't see it as a business case for that, even that use case anymore. But so like if you just focused on allowing user space to be Big Endian, is that something that you're still getting a lot of pushback on that? I mean, how much of the kernel does that affect?
So we are getting a lot of pushback from a lot of things, and until there's hardware to support it, basically the kernel have said they don't really want to maintain it. So until we see hardware that supports this configurable runtime endianness, we're not going to see any support in things like the kernel.
Okay, but I guess I'm just more specifically, if you ignore, like if we say, hey, OpenSBI little endian, kernel little endian only, that's all it is how intrusive are the changes to with hardware support to just say only support configurable user space and everything else is little endian unconditionally?
So these changes that we come up with are not intrusive at all. The entire thing is very small in terms of like the actual, if you look at the line changes, I don't know if you can remember the numbers, but it's but the actual changes they're making aren't intrusive.
Well, right. But I guess that even if they're not intrusive, if you are now adding another config option to the kernel, that adds testing and all this other stuff. I guess that so there's maybe intrusive is the wrong word, but and anyway, I think that's probably the only use case that actually exists in reality would be Big Endian user space.
I think I can help with this one. So it's not quite that we have with the kernel that you can swap. So the kernel completely does not support having a little endian kernel and then a Big Endian userland.
Okay.
So that was one of the things we think could be possible in the future and might be a useful case. Largely, we did this as R&D. But what we did was we switched the entire kernel to Big Endian, in which case the changes were fairly unintrusive.
Okay.
With looking at what it would be like to disconnect them and have them running in different endiannesses, we didn't look into, but we thought it would be a theoretically interesting idea.
Yeah. Okay.